All right, guys, let's get started. So, people are coming in. All right, so there, and we are just going to get started with the topic for this week. So if you remember last week, we started talking about DNS, right? And hopefully you've been working on setting up the DNS server, your VMs, a couple of VMs for the lab this Thursday. This Thursday in lab, I will cover the DNS attacks. Please mute your microphones if you can. So this Thursday, we will cover DNS attacks. And today in the lecture, I'm going to introduce a new topic called MapReduce, basically. So this is a very interesting topic so that we're going to learn about. And basically, it relates to cluster computing. Okay, so we're going to start talking about cluster computing. If you remember, I said, you know, you're working on the DNS lab, right? And that's your first intro to kind of a somewhat complex configuration. At the end of the semester, you will have to configure a much more complex system, right, in Linux, which is going to be called Hadoop. I'm not going to give you any documentation for this, okay? I will simply say, you know, build a cluster of at least 2 Linux machines using Hadoop and then process some data. Okay, so what I'm going to do in the lecture now and next week is just basically give you all the how it works, you know, the ideas, and then after that you guys will have to do this. Remember, this will be part of your term project, which will be 5% of your grade. Right, so I usually call it like project A or project B of the semester. Okay, it should be a very interesting topic though, as we will be talking about, you know, Hadoop is actually a tool in Linux. So it's an implementation. But actually the main concept is actually called MapReduce. So MapReduce. This is, if you will, like the underlying principles of it all. And then based on those principles, people have developed different solutions that you can have, including one called Hadoop. Right, so I always do this in the semester. Now, Hadoop is basically it's a cluster computing architecture, right, to configure multiple machines as one single machine. So you have individual PCs, PC1, PC2, PC3, and basically you're going to link them together to be a specific system. Okay, So this is, you know, the cluster basically that you're going to build, where you're going to have one that is, you know, in charge, basically the main agent, and then you're going to have the managed agents, basically. All right, so the manager and the managed agents, and then you have, you know, this basically we need to process some data. So you're going to have a specific problem. Now we can not every problem out there can be handled by MapReduce. Okay, only certain types of problems can be handled, but you have to kind of put your data in the specific format, right, to be able to process the data. So what is the idea? The idea, I think I mentioned this last week, that you're going to be processing data in parallel. Okay, so you're going to be processing data in parallel, which means that, and that's where MapReduce comes in, because MapReduce is an approach, you know, a way that you can, you know, organize things to be able to process in parallel. And at the end of the day, what you want is the advantage that, in theory, you know, by having a cluster and sending, you know, taking the data, breaking it up into pieces, in theory, you're going to do that, and every member of the cluster gets a piece, so you can reduce the amount of processing time. Okay, well, the simplest problem that you will get for this will be a counting problem. Okay, so counting problem, we could write Python scripts for this, or you can use the built-in Java applications. The thing that I need to see basically is that you build a cluster of at least two devices, right? And that you show evidence that you are in fact able to run a job in the cluster itself, right? But that requires configuration of Linux, okay? And it'll basically bring together a lot of the things that we've been doing this semester, okay? Does that make sense? So that's the basic idea. So today I'm gonna go into the theory, if you will, of MapReduce itself, okay? And we're gonna talk about basically the design specifications of something like MapReduce. Why would you have something like this? So we can start basically with the question of what do we want, what we want to do. Okay, so what is it? What do we want to do? So, you know, the story goes that Amazon, right, needed to had a lot of servers, right, to support their function of selling products. And then during Christmas, the demand would go up really high. And then they had enough servers to cover the year, but when Christmas came around, they just didn't have enough servers. So what does Amazon do? Because they don't want to lose business, they increase the number of servers, right, for the volume in during Christmas. But then what happens during the rest of the year? They have all these machines that are not being used, standard Linux CPU boxes, right? And so they're all this infrastructure is not being used. So then they figure out, well, we've got this entire investment. What do we do? So, you know, cloud computing was born, right? So simply, you know, start, you know, build an infrastructure to coordinate all these devices. And that's how, you know, that's the story, right? And then cloud computer is born, and then you have all these servers sitting down, and you want to process large amounts of data. So what do? You link together the computers because they're just sitting there. You guys see that? So that's kind of the where all of it, I mean, basically where all this comes from. Google, same thing. They want to be able to process all this data, right? And but they have a lot of data to process. They have, you know, massive server locations, right? So the same thing. They're processing data. They have it's almost like they already have all these servers. So what else can they do with it? Well, why don't we just put them in parallel and do the processing like that? You see that? And so that's kind of where cluster computing comes from. There's a couple of ways of doing parallel, at least. The two main ones are going to be the CPU-based solutions, like cluster computing. And then there's what are called the GPU which is basically processing your data on graphics cards, like the NVIDIA graphics cards, right? Those with GPU solutions, you actually just need one machine. If the motherboard can support 2 or 3 GPUs, that's a lot of computing power right there. Google, probably has motherboards that support 8 of really powerful GPUs, but certainly this is one approach to parallel computing that's very popular. But there are other approaches like I said, like this CPU one. And usually this will happen, as I said, when you already have the capacity. You already, like here at the university, think about it, right? Think about all these computers, right? They're not always being used. If you think about it, they're on sometimes, right? And there's nobody in here. So if the university wanted to maximize its investment, they could install software on them, cluster them, and then start doing cloud computing. Do you see that? They just don't need to do it, or don't have, they're not doing it, but they could. And so that's kind of where cluster computing kind of comes in. It's like you have the available hardware, and so now how do you put it to good use, right? And so one, there's cloud, but also combining the equipment. All right, so that's really, what do we want to do, right? So you hopefully you understand the motivation. So I will not cover GPU in this course, right? We will just focus on CPU. We do have a class, I think it's 470. It's an elective, and you can talk to Professor Tae-Hoon Kim about it. I think it's called High Performance Computing, something like that. It's an elective course. You can definitely learn more about that. Now, the difference between that class and this class, obviously, this is an intro. This is only, basically between second year and third year. I'm only going to introduce the topic of cluster computing and MapReduce, and from the point of view of a sysadmin. You're not going to develop software to link computers, right? We're only going to use software like Hadoop to link them, right? So what is it that you're going to do? You're just going to configure, right? You're going to put on your sysadmin hat, your Linux guru hat, and just configure. Do you guys see that? And then after that, you're just going to solve a very simple problem. In his course, he'll do software and many problems. But if you like this topic, certainly talk to him, because I will only spend a couple of weeks on it at most, and then the project and then we'll move on. But it's an intro, as I said, to the topic, which I like. It's interesting. All right, so let's go ahead then. So we know now what we want to do. We're gonna use this infrastructure to solve problems. So there's gonna be the configuration, but also the coding part, right? So you're gonna either use built-in programs written in Java, maybe, or you can just write your own programs. One nice thing about this is all that redirection that we talked about before, like the piping and everything, we're gonna start using that even more. And just see the power. Remember that Linux itself, the terminal, can help you to solve many problems. You can literally solve a lot of things just on the terminal. All right, and so there's a lot of functions built in beyond the ones that I have mentioned. And one thing about those functions in the Linux kernel is that they're the fastest. Right, they are like you're not gonna find faster things, to process what you want. So you do leverage that aspect of the Linux operating system. Okay. So we will also have to learn a little bit how to write a script, like the Python scripts that we've been writing this semester, but for parallel computing. When you have parallel computing, it's not the same programming. Okay. That applies for both GPU. That applies for both GPU and CPU. Okay, they have their specific ways of doing things. Usually for GPUs, you use something called the CUDA library. I don't know if you guys have heard of this. C++. Right, so but there's a lot of abstracting libraries that help you to use the GPU without getting into CUDA. But this is tough, actually. writing it in C, C++ in parallel. However, as I said, we're not covering GPUs, we're only covering CPU, and we're only going to look at like Python, so very high level. But at the same time, we still have to think a little bit differently about how we're going to code because it's in parallel. All right, but anyway, like my goal with these lectures is usually to kind of lay the foundations, right? So that you understand the big picture of cluster computing, and then we can build from there. All right, so let's go to the next slide. Okay, so the problem, keep in mind, you know, think of a problem, so it'll be a word count. So we're gonna take some books from the Gutenberg library, I'm sure you've heard of it online. We're gonna download the books, and all you're gonna do is count the words in those books. Now, that's a good problem for parallel computing, right? Because think of it as, I grab a book and I rip like the 1/3 of the book and I throw it over there to you guys, and then I rip another third and I throw it over here, and then I give you the other third, right? So you guys can then tally the words in your third, have the summaries, and then when you're done, and when you're done and you're done, we aggregate. You guys see that? And we do that in parallel. That's exactly how you do parallel computing, right? Except, you know, you want to be more efficient than just ripping 1/3 of a book, right? But so we're going to think about that. Now, remember, one big factor is that if you're sending data to them, and you're sending data across the internet, network connections are not as fast as the bus on the motherboard of a computer. Okay, the computer bus, right? On the motherboard of a computer is much faster. RAM is much faster than sending data through the network. That's, you know, not efficient. Packets are dropped. Imagine if you're sending like a ton of data and then one packet is dropped, what happens, right? So there's a lot of issues with that in the network side. Okay, and you know, when you do the configuration yourself of Hadoop with the cluster, you will see that you have to do some network configurations. You'll have to use SSH, you know, things like that. Okay, I think I did say that you can work on that project in groups of 2, so that should be fine. And then you'll do your presentations at the end of the semester, which, by the way, is coming up really quickly. Okay, keep that in mind. This is week 8. Spring break is just around the corner, and then boom, we're almost done. So make sure after this lecture that you start thinking about that. The problem will require you to install Hadoop on 2004. And like I said, I'm not going to provide any documentation. So really, you have to go online. You have to find Hadoop current version for 2004 for the multi-node. So there's going to be descriptions on what is called single node, and then there's going to be descriptions on multi-node. Now, I provided some documents on Brightspace, but it's for an older version of not 2004. So again, I'll say this: you should not use those documents. You can read through them just to get a feel for them, right? That's actually a good idea. Read them, get an understanding of how it works, but then you need to find the specific version for your specific operating system. And that's something that you're always going to have to do. Think about it, you know, by the time you graduate, 2004 will be history, right? And there will be another Linux version. And that'll, you know, things that just 5 years ago are no longer supported, right? So that's how Linux, the ecosystem of Linux works, right? So, you know, it comes out and then it's not supported anymore. And then things are going to break whenever you're running commands. So you have to kind of get used to that. But the great thing about it is the Unix philosophy is always maintained, right? Always maintained. So yeah, so the program then will read some text files, like I said, from the Gutenberg library, and we'll do basically a tally of all the words in that document. Okay, and then you will have to demo that at the end of the semester. You have to demo that you did it successfully, and also that you ran it in the cluster itself. So I have a few commands that I can run on your cluster that will tell me if you actually ran it in parallel or not. Does that make sense? All right, so that's the problem. So we'll use the Hadoop API. So we'll use, as I said, we'll use Python. We will basically use, on the terminal, we'll be able to call Hadoop, for instance, right? And then Hadoop will output something that we'll be able to pipe into some Python script, right? And then, be able to process it further, right? So we're going to be using a lot of redirection to make these changes, to send from a program to a Python script and vice versa. We will use the built-in streaming API. So we will use the streaming API. And all of this should be on the Brightspace environment, by the way. The streaming API, which basically is the standard in and standard out. So these are ways that we can get data from the terminal into a program and vice versa. All right, so now let's get into the big picture of MapReduce. So let's get into the big picture of MapReduce as a concept. So what is this? So if you look, actually, it's made up of two words, map and reduce. All right, and it simply means in parallel computing, you're going to do a lot of mapping. And then once you've mapped things, you're going to do a lot of reducing. Okay, so that's kind of where that name comes from. Is, it's like, this is what we do, and that's what we call it, right? So the idea is that data, the mapping part means that we need to format the data for parallel processing. Okay, it's almost like we have to take whatever data we have, make it into packets, and send it out, right? And then, it's kind of like that, similar analogy. And then the reduction is basically once we process everything, we summarize it or aggregate it, etc. So before we talk about MapReduce, we are used to, of course, single node architectures. So you don't actually see a lot of clusters around here, right? So you usually see just a whole bunch of nodes, individual nodes. And the key aspects that we need when we think about single node is that we need to break it down now into the CPU and the memory. Okay, so this is really what's important, because we're going to start treating CPU and memory as like units, as very small units, right, of computing power and storage, right, or memory. So, one of the problems is that you might have is that the data is really big, right? So like if the data is extremely big, it's not going to fit in one single node, right? So then it has to be broken up into parts, right? And this is usually referred to when we break data, when we break data up, this is called a batch. Right, so we're going to be talking about batches and just breaking the data into these batches. So now, a cluster is basically, or can be, a just several computers put together, right? So you might think of a rack or something where you're going to have several machines all connected to a switch or some other device like that. Right, and this, of course, with your VM, with VMware, you have like a built-in hub or a built-in switch in VMware, so you can connect at least a couple of computers. Right, you just have to make sure that you can ping from one to the other, that you have all the information. But really, what's going to become more important when we think about the devices is just thinking about the individual pieces of the CPU, the memory, and also the disk, the hard disk, right? Because these are actually the problems that we have to deal with, right? We have to deal with the fact that we need to store the data more permanently than hold it in memory, right? And then process, right? And so that's what we have to think about. So, Google, for instance, probably has 10 million or who knows how many, probably more than that actually, nowadays, computers clustered together, right? So if you think of the whole of Google, and that's just Google itself, they have so many servers. I think you've seen the pictures in some of the slides, right? I have pictures of data centers for Google, and you'll see they have like almost containers, like those 18-wheeler type containers, where they have all the machines clustered together. So if now that we're going to think about this idea of MapReduce, right? So we have MapReduce, which we've determined that's going to be the approach to parallel computing with CPUs. So we're going to build a cluster. But before we build a cluster, we want to consider what would be the issues, right? What would be the problems with trying to build something like this? Because those problems actually will dictate how we design this. If you think like what Google did or what Amazon, et cetera, AWS, before they started designing the solution, MapReduce, Hadoop, they wanted to consider, okay, so what are the issues? So let's just say the issues. Oops. Issues with, okay. Okay, so issues with cluster computing. So think about a scenario where we have 100 to 1,000 computers, right, available. We're gonna bring them together somehow, right? And these machines should all work together to count words. So we have all this data, it's really big. So we have issues of we have to store the data, we have to move the data, we have to process the data, we have to aggregate the data, right? So all these things we have to consider. So, but at the same time, we have to consider things about the infrastructure that we are building. For instance, one of the main things that we have to consider is, and also, by the way, we're going to refer to these devices from now on as nodes. Okay, so these are going to be the nodes in the network. Okay, so these are the nodes. Okay, that, they just represent these units, right? So one of the things that we need to consider is that nodes can fail. What do I mean by that? I mean that you build a cluster out of these, several of them are going to stop working. That's just for whatever reason, whether it's a mechanical, electronic thing, cable becomes unplugged, something stops working, and the computer or software issue, etc. Right? So the nodes can fail. So when you define or design this implementation, you have to design it in such a way that it is robust to the failure of a node. Do you guys see that? So there's got to be replication. What does that mean? It means that if I have a piece of data that's key, I can't just have it on that computer, because they have the whole cluster, it's all working fine. That piece of information fails, you can't finish the job. You see that? So what do you need? Replication. That is to say that a little piece is there, but there's a copy in the other machine. So to minimize the probability that you would damage the whole system, okay? Or the whole job, let's say the whole job. So for instance, there's a nice statistic out there that says that if you have 1,000 servers in a cluster, or in clusters, maybe it doesn't have to be one single cluster, in clusters, you can expect one failure per day. So you can expect one failure per day, just when you have 1,000 servers in a cluster. Okay, so that kind of gives you a number of the failures. So then, of course, if a node fails, So if the node fails, then you need to deal with the issue, okay? Now, a second challenge. So a second challenge, let's say, of the issues of cluster mapping. Right, let me add a. All right, just checking that that's working. All right, so the second issue that you might have, another challenge is, as I said before, the network bottleneck. Okay, so the network bottleneck. You know, think about the fact that you're sending data. You know, this computer is going to do a good job sending it through the network to another computer, right? So there is that issue, the bottleneck, the bandwidth, basically, of your environment. Okay. So here's another statistic. With a network bandwidth, let's say a bandwidth of, so network bandwidth of 1 gigabits per second, right? If you need to move, so assuming this bandwidth, then moving 10 terabytes takes about 1 day. So you have to understand that we're talking about serious scale here, right? Serious scale in data amount. So obviously, assuming a specific bandwidth here, and you're moving, let's say, about 10 terabytes, that can take 1 day, let's say. So obviously, when you're moving a lot of data, you know, if it's taking a day, that that's really slowing down the job. Okay, so just designing things like, oh yeah, I'm gonna have these 3 computers do this specific function, and then when I'm done, all the data needs to go through these 3 and then go to the next step. That's probably inefficient. Although that intuitively would make sense, it's not a good idea actually to move data through the network. Do you guys see that? So because of this, because given a bandwidth, so you don't really, the numbers are just there as an example, but what's really important is, given a bandwidth and an amount of data that needs to be moved, it's going to take a specific amount of time. It's going to slow down your job. So you need to find, when you design this, efficient ways of storing the data without sending too much data through the network. Do you guys understand that? That's one of the key ideas. So we'll come back to that one shortly. Right now, I'm just talking about some of the issues. So you need an architecture. So you need, for number 2, therefore, let's say, you need an architecture that does not move data too much, right? So you need an architecture that does not move data too much. This is important, okay? This slide, I would recommend that you make a note that it's important, because this is usually a question I ask on the exam, okay? At some point later in the semester, when we have our second exam, what are the issues of cluster computing? So what are they? Nodes can fail. Number 2, the network bottleneck, okay? And then there's a third one, of course, but that we'll talk about in a second. The third one is actually the programming of this. Programming. Okay. Sorry. All right. The programming of this is no longer like the programming that you've learned. Okay. So all the programming that you learn is going to contribute, but you have to think different. whether you're doing GPU or you're doing cluster computing, because now you have to think in terms of these issues. All of these issues, network bottleneck, nodes can fail, just breaking up the data, processing things efficiently, all of it requires a new paradigm, if you will, of coding, all right, which is, is sometimes referred to as parallel programming or distributed. So I think distributed is the terminology used for the MapReduce environment. So basically then let's say distributed programming, which is what this means. We have to distribute out, think about it, right? Now I'm saying I'm going to process this on every machine. So that function or that piece of code needs to be sent out to all the machines, right? So that's called distributed because you're distributing out the program. Now the program, when I say the code, or that it could be a process, right? It could be a process. Remember that a process is just an instance of some software or firmware, right? So it can be any one of those. But the third issue basically with cluster computing that we want to state is that distributed programming is hard, actually. Hard and can be really hard if you're not paying attention. So you want to also simplify this as much as possible, right? By having a specific way of doing it. Okay, so you need basically, a simple model. Simple model to hide the complexity. So sometime next week, probably, we will go over this last one, the distributed programming, and you'll see what I'm talking about. We will just try to, I think, count some things or something like that, and you'll see that it's not exactly trivial. And we're just counting. That's all we're going to be doing. All right, so now the great thing about this is, so again, I want you to kind of think about this historically. You're at AWS or you're at Google, and you have all these servers, and you have these goal of cloud and putting things together, but you've identified, as the story goes, you've identified, well, nodes can fail, so that's a problem. Network bottlenecks are an issue. Coding this is hard, right? And so how do we address it? So they thought about it, really hard. And there's many solutions. There's other solutions, I should say, beyond Hadoop, right? It's only one of them, certainly one of the most popular ones. But before Hadoop, they came up with the framework, which is, as I said, MapReduce. Okay, which is basically an approach that hopefully handles all these issues, right? So it allows you to create this framework for cluster computing, okay? So let's just say that MapReduce, addresses all three of these challenges or these issues. So now we're going to think about is how does MapReduce actually address these challenges? Okay. So now let's go in and kind of state, so how is it that MapReduce addresses this? So how do okay, so let's say, so let's, MapReduce addresses all these three issues, and how does it do it? So number one, let's just start like that. The first issue was, if we go back, nodes can fail, right? So nodes can fail. On the issue of nodes can fail, what does MapReduce say that we should do? Basically the answer is that we store data redundantly. Okay, so we're going to store our data redundantly. Okay, so replicate the data. Okay, now the data will be pieces of very tiny pieces of information. The idea is actually not to store large amounts, you know, like big pieces, but instead to have smaller pieces of data that can be easily replicated. So store data redundantly on multiple nodes. So notice not just two, but on multiple nodes for persistence and availability. All right, so on multiple nodes for persistence and availability. Okay, so that's an important one because that dictates exactly what we need to do. And in fact, Hadoop has what is called the HDFS, the Hadoop Distributed File System. And what the Hadoop Distributed File System is a mapping of all hard drives into all the hard drives of the computers that are using Hadoop or MapReduce, map into one common distributed file system, Hadoop file system. Now, keep in mind this distributed Hadoop distributed file system, HDFS, does not actually exist physically, right? It is a virtual hard disk, if you will, made up of all the individual ones. Does that make, yeah, go ahead. Say that again, sir. So the Hadoop, so when you start Hadoop, you have to create the files, the Hadoop file system. You have your data in the physical hard disks, and then you upload it to the Hadoop file system. Here's the thing, you don't know where it's going to put it. Do you know what I mean? That's something that the software should do. So there's two copies. There's the physical original copy, and then there's now the uploaded to the HDFS copy. You see? There, yeah, so you upload one, and you will do this actually when you do Hadoop. You'll have some files in the hard drive, but then you're going to say, okay, I created Hadoop, started the cluster of at least two. Obviously, you would probably want to have 1,000. More, yeah, more than two. And then now that you're ready to do a job, you're going to take the job from the hard drive, upload it to the Hadoop distributed file system. But where does Hadoop put this data? You don't know. Should you be concerned that it's, so your concern was, what if you delete it? Should you be concerned? No, because actually nodes can fail actually applies to, I can delete it by accident also. And do you see that? And so the data should be what? Store the data redundantly on multiple nodes for persistence and availability. I mean, that's the goal anyway. Do you see that? Yeah. And so that's what I was saying, that it seems simple, right? That the idea, but implementing this as a software solution takes a lot of work. Okay. But yeah, so you only process your jobs from the Hadoop distributed file system and not from the physical machine. Okay. Any other questions? Yes, sir. Go ahead.
This one, if a node does fail, wouldn't it still cause problems?
How so?
Since it's storing it redundantly, if it fails in the middle of a job, it won't matter if it's redundant, if it's not complete. There's some sort of verification done.
There's another version of it, right? Of the data. Okay, so there's that one has a piece of that, has this data, and that one has the same piece of data. If that one fails in the middle of the job, it'll say, I couldn't complete the job. And there's a manager that will record that. And so then they can just bring up the other one until they complete the job. Does that answer your question?
Yeah.
So again, CPU time is going to be called compute or processing, and storage, you know, it's the distributed file system, the Hadoop, and then there's RAM. You treat all of those really like little processes running on all machines. You see that? And they're all handling their little piece of work. When they finish, they report back. I finished, no errors, you know, and then you aggregate. That's why it's called MapReduce. You see, so first you map the data into the specific format, like distributing it job is done. When it's completed, you're gonna aggregate it, reduce it, piece it together somehow, and that's the reduce part. And that'll become obvious even in the coding, because we'll write two scripts, a mapping script and a reduce script. And that'll actually be very useful to understand how that works. Even though we're not like implementing the Hadoop software itself, by understanding the scripts, we'll get a sense of how it works underneath. Got it? Any other questions? Nope. All right, yeah. So this is important, right? So nodes can fail. So you store data redundantly on multiple nodes for persistence and availability. And this hopefully will become a little bit more obvious as we move further. All right, so we're talking about how does MapReduce address all of these three issues. Okay, so let's move to number 2. Number 2. And we need to go back actually. And what was 2? What was the issue? What was the issue? The network bottleneck, right? So you see that here. So we said bandwidth of 1 gigabits per second when moving 10 terabytes can take up to a day. You need to work that into the equation, right? Instinctively, I guarantee you guys would say, let's grab these 10 computers. They just do this. When they finish, they'll send it over there. Good enough. I'm going home. You know what I mean? So that might be the way that you would think about it, but that's actually still inefficient, because what you're suggesting is, let's grab 10 terabytes of data, send it there, process it, and then let's grab those 10 terabytes of data and now send it all across the network to that other group. And that's not what you want to do. Okay, you want to have a different philosophy from that. All right, so then we're going to think about what MapReduce actually does in number 2. So number 2 is the network. The network is actually very limiting because it doesn't compare at all to the, as I said, the bus of a motherboard, right, in speed. So then what is the solution? The solution is basically, it sounds simple, but to say, but that this is the solution. Move computation close to the data to minimize network transfers. So how close can you move computation to the data? What would you guys say? Because it says here, it's kind of just says move computation close to the data to minimize network transfer. So what do you think that means? Computation is what? Computation is grabbing some data and running some function, and then you get an output, right? Yeah, go ahead, Lenny. Mm-hmm. How close can you get? Exactly, very good. Yeah, yeah, great job. There you go. Exactly, so that's exactly what you do. The closest that you can get to the compute, well, the CPU is on the device. So the data that CPU will process, let's store it there. Do you guys see that? So basically when you're doing MapReduce now, you're going to have two processes. One process that handles the data storage that is linked to the HDFS, and one that is linked to the processing, right? The whatever the CPU, the computation that it needs to do. Both of those should be on the same machine, so that you just one time move the data. Because think about what I'm, let's say I grab 10 terabytes of data from a hard disk or a hard drive. I load them into the HDFS. The HDFS then, boom, sends a little piece to every one of these machines, replicates and everything like that. Then the computing, you send. Instead of grabbing data and sending it to a compute machine and then back, it's like almost you put the data there and you send the compute to it. Do the computing there and then only send back the aggregation. Got it? So that's basically the idea. So you move computation close to the data to minimize data movement. You really, that's one key thing. You want to send, you don't, once you put the data in one piece of the HDFS, you do not want it to move. Okay. And you only send out results, which should be a lot more. Think about sending an entire book versus just the sum of the, right? So the might appear, 10,000 times in a document, right? So do you want to send a document with 10,000 thes in it, or do you just want to send one line that says the equal 10,000? It's a huge saving, right? And so that's basically the idea. And then number 3 is the, as we talked about, the distributed programming. Because obviously, if you're building a cluster, it's for it to do a job, right? So it's for it to do jobs, whether they're built in firmware or software of some kind, or code or whatever it is. So distributed programming. Okay. So you want to hide the complexity as much as possible, right? And so here, what we're going to learn is that we're going to follow a pipeline. I'm going to simplify it quite a bit, but it's a pipeline where we're going to say mapper.py, which is the mapping function. And then we're going to pipe it into the reducer.py, if that makes sense. So we're going to actually do the code, the mapping as one script, and then the reducing as another script. And we're going to take advantage of the terminal to redirect, inputs and outputs. And we can build very long pipelines like this on the terminal itself. We can do things like sorting. I don't know if you guys knew that you can actually sort data in the terminal and take differences of data. All kinds of things can be done nicely. All right, so now this is how you address these things. Now let's take a look at the redundant storage infrastructure. So just briefly, so the redundant storage infrastructure. Okay, so this, as I said, comes down to, in Hadoop, this will be the Hadoop distributed file system, or HDFS. Okay, which, like I said, it's a virtual representation of the physical device. So it's a distributed file system, which provides a global file namespace. Okay, where it provides redundancy and availability, which are the things that we want for it. So things that are common for the HDFS is that reads are common. Reads are common, so you can read the data, but you don't update the data, right? So basically, not that many updates, let's say. So not that many updates. And what that means is that once the data is written down, you don't touch it again. That's basically the goal. That should be your goal, in fact. Once the data is there, don't update it again in the system. So the distributed file system, then, we can say over here, so the distributed file system, data is kept in what are called chunks. Okay, so we're going to divide the data into chunks and spread across machines. So number one, you take the whole data. So data is kept in chunks. Now, again, remember, not all data can be divided into chunks and be processed in parallel, right? Just some of it. But, you know, something, as I said, the example of counting words is a perfect example of something that can be processed in parallel. So data is divided in chunks. Number two, each chunk is replicated. So each chunk is replicated. Okay, so for instance, here we have, you know, you're going to have multiple servers, and then the servers are going to store data. So let's imagine a simple scenario, and this should be pretty straightforward. Let's say that we have a file. This is an example. It's an example, and we have a file. And let's say that the file, you know, is kind of like that, buffer and memory, right? We're going to divide it up into parts, C0, C1, C2, C3, C4, C5. Those are the pieces of the file. So now, do we have to do this? We don't have to, right? All of this is handled by Hadoop itself, right? So that's the nice thing about this is this, you know, this would be very difficult to do. So this will be handled by Hadoop. I think if you guys take Professor Kim's course, then you have to do this. Like, you have to do it. But in here, we just use something like Hadoop that does it for us. So then now we have several chunks, right? Which are let's call them chunk servers. So this is, you know, chunk server 1. And then let's just do like 4 of them just to drive a point. So I'm just going to say chunk server 2, chunk server 3, chunk server 4. Okay, and now you take the individual pieces of the file and you're going to store them and replicate them. So C0 is stored there, but it might be stored over here. Now, these are parameters that you can set up in your environment to decide how many replications you're going to have. And then C1, so notice you can actually have multiple pieces of the file, right? It's not like you just have to have one piece of it, you know. And that means that there's a process associated with them as well, right? So it's basically like you're sending that chunk with its corresponding processing. Remember that the goal of Hadoop is to actually process data, not so much storage of data. It's not like a storage thing, right? The storage is necessary, but it goes tied in with the processing as well. And then here you have like C1, and then over here you might have C1 again. So notice how you have it distributed. You have one managing computer, right? Managing computer that will keep track of where things are. But what's important is that chunk servers also serve as compute servers. All right, so what this means is that this chunk server is also a compute, because the computing is computing, and so the storage of the data and the processing of the data are basically reduced to just a process, right? So basically you have a running process here for the chunk part, the distributing, the managing of the data, and then you have another process for the computing of the data. Okay, so that's kind of the architecture. So that's what you install on the individual machines, is those agents that handle that processing for you. Okay. Does that make sense, guys? Are there any questions with any of this so far? So as I said, this is just the overall high-level view of MapReduce. Okay. Let's continue here. So we're gonna do, I don't want to do any of the coding today. Yeah, so I'm not gonna do the coding today. And instead, we're just gonna focus on the high-level architecture, if you will, right? right? So I just want you to understand really well what MapReduce is, what the Hadoop environment is, before you start implementing. So now let's think about this idea of how you map and reduce information. Okay, how do you distribute the data? So probably we'll need some kind of an example for this. Okay, but that should, and this will literally be how you do it. When you count the words, you're going to have to do this. So you have the cluster. Now imagine that you have a cluster. That cluster will have chunk servers. Chunk servers, which will store data and compute. Or data and processing, however you want to call it, computing. Okay. All right, so you have that. This is sometimes called, and then you need to have the main or the managing node, the managing, right, node, which is sometimes referred to as the name node in Hadoop. So the name, and this can change, but the name node in Hadoop itself. So what does this one do? The management node stores metadata about where files are stored. You know, the individual chunks. It knows also the job that needs to be run, and then it's in charge of distributing all of that and aggregating the information. And the management node can also be replicated, right? So can be replicated as well, which makes sense. Later in the semester, after spring break, we're going to look at a protocol for network monitoring called SNMP. Pretty similar architecture. There's going to be agents and managers, and this has been historically the traditional approach to monitoring, monitoring protocol, if you will. Right, so we'll take a look at that one as well. But they're all very similar, right? They have those common similarities. So the best way to understand. So now that we're here, we want to understand, how does MapReduce work? Okay, so this probably is slightly the hardest part, but it's important that you start to get the logic behind this, because when you do the coding, the algorithms, they will be based on this, the MapReduce framework. Okay, so let's imagine an example. So an example, we have a file. We have a file, .txt. Right, imagine it's from the Gutenberg library. It's got a story like Huckleberry Finn or something like that, right? And the problem, I'm taking something pretty intuitive and simple to understand. We just want to count the words in that. That's it. So don't lose sight of that. So then what we have to do is we have to first take the file. So we want to take the file. Let's say cat file.txt, right? And then we're gonna map it somehow, right? So we need to do the map or mapper, however you want to call it, but we need to do that function. So the question is, how do we do that? All right, so let's think about it. So the mapping would be first, just kind of pseudocode overall kind of idea. The first thing is we want to scan the input file. Okay, we want to scan the input file. And then this is the thing that is very specific to the MapReduce. We need to somehow format that data in a way that it can be distributed. Okay, in a way that it can be distributed to a cluster where the devices are in parallel. So here we're scanning, let's say one line at a time. One line at a time. Okay. And now we need to convert this data into key value pairs. Key value pairs. Why do we do that? Because by breaking it into key value pairs, we convert them into basically these little units. And then we just can send them out and forget about them and not have to keep a record of where the was found in this story or whatever. Now, keep in mind, this is for the specific problem of counting words. A more difficult problem might require more creativity in your mapping. So I want you to understand that this mapping that I'm doing is the simplest that we can think of. There might be more complex mappings, but the idea will be similar. Hopefully that's really what you have to get. So the idea is that we're going to create keys, and then eventually we can group things by key. All right, so that is to say, we have the word the in a document and it appears 10,000 times. So we create 10,000 key value pairs where the key is the and the value is 1, because we saw one instance of it. We send it out, and that's the unit. That's the key value pair. Later on, when all of you report back your tallies for the, you all have the same key, the. And so I can aggregate based on that. So that's the basic logic that we can use to accomplish something like this. So we are going to, let's summarize it here. We're going to break into key value pairs. Key value pairs. Oops. Okay, and then we're going to group after the processing probably, or during the processing, but we group by key. So that's really the advantage of how we send the data and the formatting. Once we have them grouped by key, then comes the reduce part. And basically the reduce just means, you know, things like summarize, aggregate. So it's really like arriving at the conclusion, right? All of you are reporting the, and now I'm going to use that group over there said the was like 500. This group said it was 700. That group said it was 3. So then it's 5 plus 700 plus 3. That gets aggregated. So that's the reduce. So in short, in its simplest form, that's what reduce is. So you have reduce, aggregate, summarize, filter, transform, right? So the basic things that you do, imagine, you know, you have some function, takes an input to get an output. Something has happened there, but it's grouping things together. So let's think about this. Here. So first you do key value pairs. So these are going to be key value pairs. Okay, so you have key 1 and then V, the value, and then key 2, whether it's just 1 or something, right? You have this association. And then we have another key 1 over here. And a value. So that that just means we have the individual keys and values. Then we group by key. So we group by key. And then now we end up with key value groups. Key value groups. So we have, for instance, K1, but now we have 1 and 2. So then you're basically aggregating the individual values and so on. So that's basically the idea. Okay. So let's now take a more concrete example. We're gonna do the word count example, because this is actually what you will have to do for your project. So this is the only, if you want to do a more complex problem, hey, feel free to do a more complex problem. The only one I'm asking you to do is the word count problem. So let's say word count example. Okay, so we're going to do the word count example. So you have, let's say, a big document, a document.txt, okay, with all the information. Now you're going to perform the first step, which is basically to map. So every single word in that document. So let's say that here you have, I'm just going to create a sentence. So the crew of the space shuttle went to the moon. Something like that, right? So you have that sentence, right? Now, and this is just one sentence of the entire document. For MapReduce to work, you have to first of all map it. So what that means is that you take the first word, the, and it's going to be one. They're all one because you're just taking every instance of it and creating something like that. So the one. Then you do crew one. Do you see that? This is actually pretty necessary, and this is the mapping. It's just making every single thing an instance that can be distributed out to someone, right? So then so that's crew. Then we do of one. The, notice again, the doesn't get added over here to two. That if you instinctively probably want to do that, but that would not be parallel computing. Do you see that? You start to see the differences? So these are the differences, right? So now here you treat this as individual things, and this is the mapping process. Then you have space, one, shuttle, one, went, one. Okay, and then you have the shuttle and went, two, one. Notice again, a third the, and it gets just, the mapping process just means that it becomes a key value pair of that instance. Okay. And finally, moon. Now, you need to add all of these, right? You need to add all of these, and you want to add them efficiently. Okay, so you end up with these key value pairs. So now, how would you go about adding these? How would you, like literally, how would you write your script, your code to add, let's say the, so you have the here, and you have the here, and you have the here. So what would you do? Now think, you have 10 terabytes of this or more. What would you do? And you have this distributed out, right, in different machines. So how would you, yeah. Yes. But you might have, let's say one machine might have this chunk. So you're saying, look for the in this document, find it, And then once you have, you know, and then now grab the next one, crew, look for other instances of it, find them, add them, and doing that. So yeah, exactly. That's, and my point is, that's how we think normally. But here, we're thinking of cluster computing parallel with massive amounts of data. So when you think about that problem, your solution is inefficient. You see that? And that's the whole point I'm trying to make here, is that there's a reason why you know, when you have cluster computing, programming no longer as you wrote it is efficient. And that's the mistake we're all going to make, because we think we've been trained to think that way. And now you guys, if you're faced with these kinds of problems, which you probably will, right? As you have more and more data and things in the world, you have to start thinking a little bit different. Yeah, go ahead, please. This is the mapping, and we know that there's 3 instances of it in this example. But now, what in the reduce part at the end, we would want the 3, right? That's what we want to arrive at. And so he suggested an approach, which would be the correct one, I would have always said, except that we are not programming as we usually do in a CPU machine. We have new considerations. The data is distributed. There's massive amounts of data. We have to do this efficiently. Do you see that? And so actually the way it turns out is, because we have mapped the words by key value pairs, before we do that count, we can actually do one step that will make this more efficient. Do you know what that is? We're going to sort the data. So by sorting the data, we no longer have to make multiple passes, right? Because in that initial solution, let's say that we have 1 million records, right? We would have to look for the word the 1 million times. Then we would have to look for the word crew in 1 million records. Then we're repeating the same thing 1 million times. You guys see that? Every time we look for a word 1 million times, and this is highly inefficient. But because we have key value pairs, we can actually sort the data first. And the great thing about this is that the sorting, we don't even have to write a script. This can happen in the Linux terminal itself, and it's going to be very efficient and fast. Okay, so then what we need to do actually is we need to sort the data. Okay, I'm going to erase this one. So now what I'm going to do is I'm going to sort the map key value pairs. So this is going to be, this is just an example. Imagine there's more data down here, right? So imagine there's more data. So then now I have sorted the data, and it's going to look like this. Crew one, right? Because we're just mapping the key value pairs that we had before, but now they're sorted. And then maybe space was only one occurrence, right? And then we have, of course, the had 3 occurrences in the previous example. And so on. So let's say shuttle, that was one of the words. ... Do you see that? So by doing this, imagine if we have 1 million records, right? Instead of for every word looking at 1 million things, now we only have to do this one time. So we go through all of them. Why? Because we know that after these 2 crews, there's no more crews. You see that? So basically now we need a logic, but we need to write this logic actually, that we look at this and we add them. Once there's a change, like this word is no longer this word, we start a new count. And that's just that one. Then once that's over, we start a new count with the, and then we have a new one, and so on. You see, but now it becomes way more efficient. And so that's the point that I was trying to make at the beginning of the discussion today, is that we build the entire framework, but distributed, the distributed file system, right? Oh, sorry, not distributed file system. Distributed programming. And we said initially that distributed programming can be hard, right? Because it's a new way of thinking. And this is actually, you have two parts to the project. You will have to configure the Hadoop cluster, but then you have to make sense of the logic that you're going to use to process things efficiently. Because just because you build the Hadoop cluster, you can still write a program that's not appropriate, and it's going to be slow. Do you see that? So you would have to build one that is consistent with the philosophy to take advantage of MapReduce. Okay, is this making sense? Is this clear? We will do next week. We will actually do the coding part. So we'll implement some kind of code without Hadoop, because we can actually do this code without Hadoop following the same logic, so that you guys have something that works. But here right now, it's really just kind of to illustrate what we can do. So, oh, sorry. No. This is where I am. So after we have done the sorting, then now we are ready to reduce. And this just means collect all, add basically in our example, add all values based on key. Now, keep in mind, as I said, this approach is only specific to the counting. So other problems might require other operations instead of adding, but the things that should be consistent are something like the mapping function, right? Some kind of a mapping needs to occur. Some kind of a sorting needs to occur. And then the reduce part. Okay, where we're going to have now, we're going to arrive at final values. Okay, so we're going to arrive at crew now is going to be 2, but we need to write, we take this input, the way that it's processed like this, and now we just need to kind of add it up. So here we have space, and I think space was just 1, and then we had the, which is 3, and then we have shuttle, which is 1, and then finally moon, let's just say dot, moon, and that was 1. All right, and that's kind of the output that happens. And all of this can happen in every single one of the machines, right? So remember that you send this data, this chunk of data, to the one individual machine, but that gets replicated. You also send the mapping logic, the sorting logic, and the reduce logic. You send all of that to the machines. And then what they need to do is they need to take the data, map it, sort it, and reduce. Once this is done per individual node in the cluster, then they can be aggregated in some efficient way to arrive at the ultimate solution. If you implement this correctly, the cluster will in fact process faster than if you weren't using a cluster. Okay. But as you can see, a lot needs to go into this. And as I've said a couple of times already today, not every problem can be modeled like this. Sometimes just some parts of a problem can be modeled like this. Let's say that you need to count words, and then you're going to use those counts for something else, to calculate some probability or something. Right? You want to predict something about the world, so you count how often certain words appear. So the prediction part may not be suitable for parallel computing, but the process intensive part of it, which is the counting, may be. So you can just focus on that part, process it in parallel with cluster computing, and then you're able to get a result. Do you guys see that? Does that make sense? Okay, so hopefully all of this, it makes it clear enough, right? That this is what you will be doing, this exact same problem. Now I will continue to give you some code in Python, and I'll show you in the Linux terminal how we can, how it actually works. But you guys will when you implement Hadoop, you can use Hadoop Hadoop has some built-in functions that can do the things for you, so you can make those work, or you can literally implement the Python as well. Okay. So just remember, in summary, you know, this is done. So I'll change color here. So this is done across multiple nodes. So this is actually, so the compute being this logic, those little scripts need to be sent out to all the nodes. Given their chunk of data, they'll do these steps and then send back a result. Okay. So that's why again, it's called MapReduce, and you usually have two functions. You know, the map and the reduce, which can literally be two Python scripts. And then we just use the standard in, standard out from there's something called sys module. And then this allows us to get standard in and standard out. And so what that does is it allows you to have the mapper of some data. So I think the pipeline will actually be something like this. So we'll do cat huckfin, let's say, right? Huckfin.txt. We pipe it. We pipe it into what? We pipe it into mapper, which could be a script. The mapper just takes from here into here via standard, the sys standard in. Then we pipe this into sort, right? To sort the data. And then the sorted data will be mapped into reduce.py, which again, we'll use standard in and standard out just to be able to grab the data into the script directly. Does this make sense? And so that's the paradigm shift in parallel computing, basically. Okay. All right. So what's left right now is the script itself. So as I said, I'm going to save that for next week. Okay, because that's going to take a long time, and we're going to need the virtual machine for that. Let me just check my notes. And I think this should already be on Brightspace. You can check there. But yeah, so today we went over the overall architecture and philosophy of MapReduce, and then we did an example, but we still need to cover some of the code. And then as far as commands and all of that, we'll talk a little bit about that next week as well. And then next week, when we talk about Brightspace, when we open up Brightspace, we will also take a look at some documents. I think I posted some links on Brightspace, which just describe Hadoop. So remember, this lecture was about MapReduce, not Hadoop itself, right? Hadoop then would be built. Hadoop is the implementation of an architecture like this, if that makes sense. Okay, so I'm pretty sure I have some links on Brightspace about Hadoop itself. So we'll cover those next week, and I'll go over that. This Thursday, we will do DNS attacks. Okay, so remember, you should have the DNS server going back to last week's lecture, right? You guys should now be done with the DNS server. Should you configure on one VM and then have another VM which uses that DNS. Remember, that's like your goal. And then I will just go over the three attacks that we were going to cover. I'll just give you, either the netwalks commands. I think we'll do it with netwalks, not with Python, and which is should be just simple commands on the terminal, and then kind of show you what it is that you have to do. All right, so I'll describe what's required, and then you should be able to finish that lab. And then next week, which is the week before spring break, I will continue with this code and just wrap up. So we'll wrap up MapReduce on that week. Go on spring break. Following, we'll start a new set of we have still quite a few topics to at least introduce to you. Okay. All right. So if you have any questions, just ask. Otherwise, this is a good stopping point. I'm going to stop the recording now.